had begun looking at the Sommerfeld's picture of how an electron moves through the solid, and the important thing which Sommerfeld realized was that the electron does not really follow the kinetic theory of gases. Its distribution is not like a Maxwell-Boltzmann distribution, but the distribution follows quantum statistics. Inside the solid you have states, energy states which are available, and the electron fills up these energy states, and the way these states are filled up is governed by the Fermi-Dirac distribution. So, there is a chemical potential mu up to which the states are occupied with a occupancy or with a probability of 1, and above it, it becomes 0. The 0 temperature chemical potential is an energy level which is close to the maximum energy which the particles have at 0 temperature, and that is what we call as the Fermi energy. And the general way to determine your chemical potential is that if you count all the number of states which are occupied, then these are all the states which are occupied up to the chemical potential multiplied by 2 particles per state, then the total number of particles, you will get the total number of particles. So, if you solve this equation, you will get your chemical potential. So, we consider that the solid is a cube of sides of length L. We had seen this already, and you write down the Schrodinger's equation for the free electron, whose energy is given by this. Ek is equal to h cross square k square by 2m, and psi k is the wave function of the electron. Being a free electron, we consider it like a plane wave. So, this is your plane wave solution for the free electron, which is moving through the solid. And you consider the solid has a finite volume, you normalize it and you get the constant, the amplitude, which is 1 by square root of v for this wave function, and then you have to put some boundary conditions on this wave function. Now, is it that all momentum states, because you want to generate the energy states which are available inside the solid. Using the plane wave, you want to generate what are the energy states available. Are there a continuum of states, or are there some finite discrete set of states which are available? And for that, Sommerfeld used the periodic boundary conditions. So, in your problem of just a single electron inside a box, you consider that the wave function becomes 0 at the 2 edges. But this has a problem because it gives rise to standing waves inside the solid, which you want a propagating mode. You want electrons to actually propagate through the solid. You do not want them to be static, and you do not want them to be standing wave type solutions. So, what Sommerfeld considered was this very important periodic boundary condition, that the wave function at x is equal to the wave function at x plus L. And this leads to solutions which are of the travelling wave form, where this is not a solution where you have nodes, but instead this is a solution. So, you do not have nodes at the edges of the sample, and if you use this sort of a periodic boundary condition in one dimension, then you will get a condition on your wave function which is e raised to I k into L is equal to 1, which gives you a condition on your momentum, that the momenta is going to be integral multiples of 2 pi by L. The net wave function psi k x y z is kx psi ky y psi k z z. So, these are the momentas in the x, y and z direction. Okay, so, we write the net wave function as a product of these wave functions, and then you can show that you can write down the periodic boundary condition as psi x plus L, y x plus L and z x plus L is equal to psi x, y and z. Namely, there is a periodic boundary condition along the x direction, along the y direction as well as along the z direction, and all of this leads to the condition on kx, ky and kz. So, let us write down the conditions on k. So, you will have e raised to I kx into L. We consider that the cube is symmetric, it has a side of length L, length, width and height are all of length L, and so if you use the periodic boundary conditions, you will have this e raised to I ky into L will be 1 and e raised to I kz into L will be 1, and this will put conditions on kx. These will give you your momentum states or the energy states. Ky is equal to 2 pi ny over L and kz is equal to 2 pi nz over L. These are your different momentum states where nx is 0, 1, 2 and so on, ny is 0, 1, 2, nz is equal to 0, 1, 2 and so on. So, these are your different momentum states. So, you generate your momentum or energy states inside the solid, which is a cube with sides of length L. And now the states that you generate, you will have to start filling up. So, can we use this expression n is equal to summation of all the momentum states, this is the Fermi-Dirac distribution, Ek minus mu, which at 0 temperature at T equal to 0 Kelvin, this expression n is equal to twice of summation of all momentum states Fd Ek minus Ef, as mu is equal to Ef at 0 Kelvin. So, can we use this expression to evaluate what is the Fermi energy of the system for this solid? If I look at the momentum of my electron in the solid, it has momentas kx, ky and kz, and these will be typically for nx, ny, you will have 0, 0, 0, you will have 2 pi by L, 0, 0, 0, 2 pi by L, 0, 0, 0, 2 pi by L, 2 pi by L, 2 pi by L, 0, and like this you will have a discrete set of states. You will have a discrete set of momentum states inside the solid. Each of them have their own kinetic energy, which is given by Ek is equal to h cross square by 2m kx square plus ky square plus kz square. So, from these discrete momenta states, you will get discrete energy states, which will then be filled up based on Fermi-Dirac distribution. So, now let us look at this momentum space kx, ky and kz. This is the 0 momentum state, which is the 0, 0, 0, and every subsequent state either in the ky direction or in the kz direction or in the kx direction, all the momentum states are spaced by a distance of 2 pi by L. These are the discrete momentum states or the energy states in the momentums. These are the discrete momentum states that we are drawing here, which we have obtained just now, and the spacing between any two points in either direction is either 2 pi by L. And you can draw what is the smallest. So, there is a point in the kx ky plane which will have 2 pi by L. This is this point which is in the kx ky plane, which will be this. Similarly, there will be another point here, and you will have another point here, and you will have another point here. So, you will have one such cube like this. There are no momentum states which are available. So, the smallest volume in the momentum space is equal to 2 pi by L the whole cube. This is the smallest volume because this distance has 2 pi by L, this is 2 pi by L, and similarly this length is 2 pi by L. Okay. You can show for yourself that this is the smallest volume. Below this volume there is no states which are available.